We're going to take a look at our next major integration technique. It's called integration by parts. It's really kind of like a reduction algorithm when it comes to integrating, kind of like long division is a reduction algorithm, right? You don't get directly to the answer, you slowly work your way to it. Well, here's actually where it comes from. If we take a look at the derivative, and I'm going to do this in differential form, of two functions multiplied together, so some function u, some function v, well, we know from our product rule that's going to be u dv plus v du. Well, if I take this sentence now and I integrate all the way through, v the integral dv, integral of v du. Well, from here, this is just the integral of the derivative, so I know what this side is. This is uv. However, since I don't know what any of these functions over here are, I really can't do anything with them. However, here's where it gets a little weird and you're saying, why would you do this? I'm going to take this piece and move it over here. So I'm going to get uv is equal to the integral of u dv, or this is actually our formula for by parts. Now, you're like, well, that doesn't seem very helpful at all, because what did I actually get? Well, this is saying if you integrate two functions multiplied together. Now, here we're assuming that this function is the derivative of some function, but it's still just a function. If we're integrating two functions multiplied together, then it's going to be the first function times, well, if that's the derivative, we're going to have to integrate to get v there. So we actually managed to integrate a piece of this, but we still have an integral to do. Hopefully, the whole idea behind the integration by substitution is this next integral will be a little bit easier to do than the original. We're kind of trying to reduce it down until we're able to integrate all the way through. Now, since this is a reduction algorithm, you can do this more than once. It's not necessarily the first time it works. You may have to keep doing by parts until you get down to something you can finally integrate. Okay, so our directions here are going to be very, very simple. Integrate. And let's just start out with, let's do something easy. Let's do x cosine x dx. Okay, you would still go through all your normal questions when you're going to integrate this. Can I integrate it directly? Can I rewrite it? Will a u substitution work? You go through all those things. In this case, what really should jump out at you when you're thinking integration by parts is, do you see two different types of functions multiplied together? See, here I have a polynomial times a trig function. So I'm thinking, well, maybe that's by parts, because that's kind of the clue there. Two different types of functions multiplied together. All right, so here's the way you're going to do by parts. You're going to pick one function to be u. So notice over here we have a u, and then everything else is going to be dv. Notice on this side, since whatever we pick to be u, everything else is going to be dv, we're going to have to integrate that to find v, and we also need the derivative of u. So u is going to be the key here on what to pick. Generally, when you pick what your u is going to be, you want it to be the function that will eventually go away by taking derivatives. If you have polynomials around, that's a pretty good guess, because you know, if you have any polynomial, I don't know, let's go x squared. If you start taking derivatives of this, eventually it goes away, right? So that's kind of the key of what we're looking for, why polynomials work well for being u. Doesn't mean if there's a polynomial there, it will always be your u, but it's a good start. So let's let u be x. Everything else up there is dv. Right, now here's where it gets confusing for brand new students here, because in the same problem, we're going to be doing derivatives and integrating. So here's u, I need the derivative of u, and again we're using our differential form, that's just going to be dx. Now over here, to get to, and most of the time we're going to leave this step out, to get to v, of course, we need to integrate both sides, right? If we integrate dv, we're just going to get v, and the integral of cosine x is sine x. Now, I know that there's a plus c here, but we're just going to tack on a giant plus c at the end that's going to take care of all of that. Okay, so here, if we integrate this, we get v is equal to the sine of x. And a quick check, remember, with your integration, if you're struggling with that, the derivative of sine is cosine. All right, now this piece here, if the function's easy enough, you really don't need to necessarily show this. If you're good with your integration, you can say the integral of cosine is sine. All right, now here's the good news. Now it's just a formula to put the pieces together. So this integral is equal to uv x sine x minus the integral of v du. You might want to say that 100 times before you go to bed tonight. So minus the integral of v du. So the integral of sine x dx. Now we're not done yet because we still have an integral that we need to do. Hopefully this integral is easier than the one we started with, and that is an integral that we should know off the top of our head. The integral of sine is negative cosine. Now since we already have a negative out front, those turn into a plus. Okay, there we go. So the integral of x cosine x is x sine x plus cosine x plus some integration constant. So integration by parts, a very, very powerful technique. Let's take a look at a few more examples. Let's say if I asked you to integrate, let's go x squared e to the x dx. Okay, so if we're going to integrate this again, go through all your questions. You know, can I integrate this directly? Will a use substitution work? All those types of questions. In this case, by parts is really jumping out at me again because I have two different types of functions. I have a polynomial times an exponential. So I'm going to pick a function u. Remember, the function u you normally pick is the function that's going to go away when you take derivatives. And that's most of the time is the polynomial. Everything else up there inside the integral is dv. All right, so once we've decided what u and dv are, take the derivative of u, which gives me 2x dx, and integrate v. The integral of e to the x dx is just e to the x. All right, good news, we are just using a formula. So this integral is equal to uv x squared e to the x minus the integral of v du. So this is going to be 2x e to the x dx. Okay, so we have part of the integral done, but we still have another integral to do. Now in this case, I can't integrate this one directly, so since I was doing by parts, I want to continue to do by parts. So for this one, actually let me write one more step here. Let's write this as x squared e to the x minus 2 times the integral. Let's get that constant out there. So for this, let's let u be. Now once you made your pick from the very beginning, we decided the u was going to be the polynomial. You have to keep doing that all the way down. If not, you're going to basically go backwards up this way. So let's let u be x, dv is e to the x dx, everything else in there. du is just dx, and v is e to the x. All right, so what we have so far, we have x squared e to the x minus 2 times. Now, since this integral is going to break into two pieces, I need to use my brackets here because this negative 2 applies to everything. So doing by parts again, we have uv, so that's x e to the x, minus the integral of v du, so e to the x dx. All right, well, we're almost done, and I'm going to finish this up at this step. Notice now that this integral is an integral that I can do. I know what that integral is, so this is going to be x squared e to the x. I'm going to distribute this negative 2 as well. Negative 2 x e to the x, negative times negative means plus 2, and the integral of e to the x is just e to the x. All right, so you notice you might have to do by parts more than one time when you are integrating here. You keep going until you get down to an integral that you can do. All right, let's take a look at a couple more examples here. Let's go back over this way so we got a little bit more room. What if I said, let's do this one. Let's do x squared ln x dx. Okay, so to do this integral, again, you would go through all your steps, you know, can you do it directly, a use substitution. Here I notice I have two different types of functions multiplied together. Again, I have a polynomial times a logarithmic function, so I'm thinking maybe by parts. So don't write this down yet, we're going to make a mistake here. So normally we let u be the polynomial, so we'd let u be equal to x squared, Everything else is dv ln x dx. Now when we go to find these pieces, I can easily du is 2x dx, but what is v, right? What is the integral of the natural log of x? Now a lot of you right now are thinking it's 1 over x. Be careful, that's the derivative, not the integral. Now, if you think about it, we actually don't know what this is yet. We've never figured out what the integral of the natural log is, which means I can't do this method by letting u be equal to x squared. So, since I can't integrate the logarithm there, let's try it the other way around. I do know what the derivative of the natural log is. See, dv is everything else, x squared dx. So du, the derivative of the log is 1 over x dx, and I know how to integrate x squared, that's 1/3 x cubed. All right, let's see if this works out. So this integral is equal to uv, so that's going to be 1/3 x cubed ln x minus the integral of v du. So that's going to be 1/3 x cubed times 1 over x dx. So 1/3 x cubed ln x minus, let's go ahead and pull that constant out front, and let's see, x cubed and the x reduced gives me x squared dx. All right, that worked because now I have an integral that I can do here. That's really the only thing about by parts is it work. Can you find the pieces up here? And once you do by parts, do you know how to do the integral that's left over? And the answer for this one is yes. 1/3 x cubed ln x minus what's going to be 1/9 x cubed plus c. All right, so as this example to show, we don't always let the polynomial, if there's a polynomial in the problem, be the u. If you have a natural log or a logarithm, a lot of times that is also u. Now that brings us into our next kind of category of by parts problems. We're going to now answer a question that we couldn't answer in that last problem. Something very, very straightforward you would have thought that we knew how to do by now. Since the natural log is one of our basic functions, you would have thought that we knew how to integrate it. Well, we don't until today. All right, so if you're going to integrate this, you say, okay, I can't integrate it directly, I can't do any substitutions, anything like that. Maybe by parts. But you say, well, hold on, Mr. Bentley. You said I do by parts when we have two different types of functions multiplied together. I only have one function here, the logarithm. And I kind of agree, but remember there's also, I know this is really subtle, we also have a 1 times that, right? And 1 technically is a polynomial. So what you do have, believe it or not, is a polynomial times a logarithm. I know it's kind of cheesy. So let's do the exact same thing that we did for this one. Let's try by parts. So if we have u is equal to the natural log of x, everything else is dv. Excuse me, let's find our derivative, so that's 1 over x dx, and when we integrate this, we get v is equal to x. All right, let's put the pieces together. uv, so x ln x minus the integral of v du, so that's going to be x times 1 over x dx, which we can simplify to just dx. Now, again, we can see that this method is going to work because we know that what this integral is once we do by parts. So this is going to be x ln x minus x plus c. Okay, so good news now. We actually know the integral of one of our basic functions. So you have two choices here. Either you can memorize this just like you do for all the integrals of all of our basic functions, or you have to memorize that you do this by parts. So let's try another one. What if I had the integral of the arc tangent of x? All right, this one will be a little messier. Now, but again, we're going to do kind of the same idea here. We don't know how to integrate this directly. Now remember, we know the derivative of the arc tangent, but we don't know the integral. When you're looking at it, you're like, all right, so I don't know it directly, I can't do a substitution, go through all your lists, nothing really works. And then you run into by parts again. Now, what kind of lets us stand out here by parts, if you have just one function there, you don't know what its integral is, but you know its derivative, by parts might work, right? Here we had one function, I didn't know its integral, but I did know how to take its derivative and notice it worked. Let's take a look at this. Here my only function is the arc tangent, so I'm going to let that be u. Of course, I do have a 1 up there. Everything else is dv. So in this case, I know the derivative of the arctangent, so du is 1 over 1 plus x squared dx, and v is equal to x. All right, let's put the pieces together and see if we can work this out. So this is going to be uv, so x arctangent of x, minus the integral of v du, so x over 1 plus x squared dx. Excuse me. All right, now the question becomes, did this work? Can we do this integral? Well, just by looking at that integral, generally once you start doing by parts, you continue doing by parts, you're like, wait a minute, I can do that integral, but I have to use another technique. Here, all I have to do is a u substitution, a regular u substitution like in the past. So notice here, again, I'm switching colors so to get, this is not the same u over here. We let u be equal 1 plus x squared, du is 2x dx. Notice that's almost exactly what we have on the top. So if I put the 2 in up there, I'd have to compensate by putting a half there. Notice that this integral now becomes, let's see, this is going to be x arctangent of x minus 1/2 the integral of 1 over u du. Right, our 2x dx is our du piece, and 1 plus x squared is u. Now we know what that integral is. That's x arctangent of x minus 1/2 natural log absolute value of u. I'm going to put my plus c there. But of course, we don't have u's in our original problem. We need to put back what this u was, because that's for our u substitution. So that is 1 plus x squared. So x arctangent of x minus 1/2 natural log 1 plus x squared plus c. Now, if you look in the back of the book, the author should have something extremely close to this. The only way he may differ is he may have parentheses here instead of absolute values. Now, we've talked about this in the past. I know 1 plus x squared is always a positive quantity, so I don't need absolute values around it. This way, the author may use parentheses because technically it is more simple or simplified. However, at this stage, I would suggest just leaving the absolute values there. It's a little bit safer. All right, so by parts is a very, very powerful technique for integration. In fact, we have a few more examples of what we can do with this by parts, but we're going to need to do that in another video.